Okay, so now to code this stuff that we did in the previous video. I've started with importing all the usual suspects like numpy, subplots, and then something from the last homework I did is I'm going to make these all dark now. And then there's something you'll notice that's new here. We have this solve IVP, which is going to, if you remember from differential equations, if you've taken that, you will know that this means like solve the initial value problem. So that's our starting point here. And then I have some variables to define. So we have like multiple tanks. So we have like area. Our first area is equal to 0.5 meters. Our initial first height, h naught 1, is equal to 0.5 meters. Not what I wanted. And then our second cross-sectional area is equal to 1 meter. We're going to make that a float. And why do you keep doing this? This is not... and then our HO2, which is not an actual compound. Don't ask me. Sorry, chemistry joke. That's my major here. And 1 point... Is this also going to be 1... Stop with this bit length. Is also going to be 1 meter. And then our third tank is going to have a cross-sectional area of 2 meters. What on earth is this bit length? That's not at all what I want. And then our h naught of 3, our third height, is equal to also 2 meters. And then we will have a set point for h3, and that is going to be equal to 4 meters. And finally, we have our alpha, which is the proportionality constant, and that is going to be equal to 0.1. And there's 3 different alphas on this, but they all have the same thing. So I'm not going to make separate variables names for those because it's not necessary. And then we have this control Kc is also equal to 0.1. And so there we have our variables defined. And am I missing anything? I am not. And so now we can start coding the right-hand side of the equation. So it's define the right-hand side. And we're going to do that in terms of time and a vector of the heights. I'm just going to put v vector because that's not what I meant to do. Sorry, I'm making mistakes all over the place. And now we're going to have our heights h1, h2, and h3 be equal to this vector. And from there, we're going to start inputting what the Q, like our flow rates are equal to. So Q between 1 and 2 is equal to, no, Q 1 and 2 is equal to alpha times numpy absolute value of h1 minus h2, and the first height minus the second height, and then that is going to be raised to the 1/2 power. I'm gonna go ahead and put these in parentheses because I do not trust Python enough. And then we're going to also multiply this by the sine function, so numpy sine of h1 minus h2. And then we can copy this, paste it, and just change the letters, because this is the exact same thing for Q1, 2 to 3, H2 to H3. Oh, I forgot to define the Qin. So Qin, or Quin, kin, whatever you want to pronounce that, is equal to AC times the set point of the third height minus third height at any given time. I don't believe that's to the 1/2 power. We shall see. Oh, I did not run this, so that's why it's giving me all this error right here. H3. Go ahead and change that. There we go. Now it likes me better. And then we have our Q out. And that is equal to alpha times third height to the 1/2. 0.5. And again, parentheses, because I never trust Python. And from there, we're going to want to return the differential equations we solved the first time. So negative Q12 divided by alpha. No, divided by the first area, the first cross-sectional area. And then we're going to want to define, and then we're going to want to return as well, because the water's going into the second tank, Q in. Just go ahead and put this in parentheses. Q in minus Q23 plus Q12 divided by the cross-sectional area of 2. No, I didn't want to enter. And then we have the third one, which is going to be our Q out, or well, our VH3, which is going to go into the surrounding area environment, is Q23 minus Q out. Oh, before I make a massive mistake, no, this is divided by the cross-sectional area of 3. There we go. And it was about to make a massive mistake. And then from here, we just do our solution is equal to solve FAP, and then we give it all our conditions, and so to start we want to give it our function, then we want to give it some bounds of integration, which actually let me get away. Let me set those up. So we've got initial and t final are equal to 0, and let's say let this thing go for 5 minutes, so 300 seconds. And then so it's going to be right, and then I believe t f comma ti, and then we want to give it our initial conditions, which are the starting heights, so H1, H2, and H3. And then the next thing is we actually want to do this with another method. Like we want to let this thing go with another method. I know. Oh, H01. Yeah, our H0s. And then we want to solve this with method, and that is going to be Radau. And this is a more stable method than the default one that Solve IVP uses. And I can show you what that does once we actually graph this. And so the next part is our dense output. We want this dense output to be equal to, I believe, true. And then this is going to be based on our solution. So dot solution. What did I do wrong? Oh, that's what I did wrong. Okay, I need to put dot solution there, I guess, to get it to have something. And from there, we want to actually make a temperature plot that is equal. So I have it, so this is going to be equal to numpy lin space, or linear space, numpy lin space, and we want from 0 to, no, well, just actually let's go ti in case we change this to the final temperature, or no, final time rather. And then since it's 5 minutes, we want it to take it every fifth of a second. So let's just say 1500 data points. Okay, so there we go. And then t equals, no, figure equals make subplots. And then we're going to want to add a scatter and then have that be x is equal to our t, y is equal to the first height. Let's just see how this one works. Okay, let's then, I guess, define H1, H2, and H3 as our solution of T. Will you work then? Okay, that's a start. So I can plot my other. Wait, why is that negative? That's not supposed to be negative. I messed something up, but let's just go ahead and add the others. See what that looks like. Okay. I clearly messed something up. Do I need parentheses around this absolute value? Parentheses love to work. It was not parentheses. Let's give this a. Let's at least give this a name. So name equals height one. So I can at least see what's going on when I do get this fixed. Do we make this into an array? Did not help. Oh, wait a minute. Did I think it's initial bounds and then final bounds. I was thinking backwards, maybe? Okay, that's what it was. It was the bounds. Okay. So I think that's what we wanted for this. And I guess I can show what happens if we make our control constant crazy high of something like 1. See, that's what happens when you make it crazy high. And then, okay, and it never actually gets to 4. Well, it gets close to 4. And so let's see what happens when we set it to extremely low. Let's just say that for funsies. Maybe that's too low. Okay, that's probably too low. Okay, it was way too low is what it was. It's not something that's possible to do. That was not expected. I guess that's why we don't make it 0.01. It does not go to the set point. I guess that's why proportional control sucks. It doesn't go to the set point. Height 1 and 2 go to like somewhere like 5, close to, and this goes to somewhere like 2.5. So yeah, and that's going to be how you plot your. It's going to be how you plot a material balance. Or yeah, this is similar to material balance. We don't have anything to do with concentration in here, so this is just a very dead simple version. So yeah, that's it for this video. Okay, just one last thing for this video. Something I forgot to mention is what happens if this, if you like have this Radu method here. So this Radu method, it's like, and I set it equal time equal to 500, and you see this is starting to go crazy over here. Say let's just set this to say 750. Oh, not 7,500. No. And that's gonna see there's like all these blips everywhere, and that's I guess because the equation can be faulty. But say we were to delete this Radu method. Okay, just for now. It would use a different method, and then you see, you can zoom in here. All this is a mess. We don't like this, so that's why we have the Radu. I guess I just have to rerun this. No. Ah, well, okay. So method is equal to RADAU and then that. Okay. Yeah. So we're just gonna have to live with that, I guess. But it's not terrible. Like I don't know if this would actually happen, but I guess in this with the point of the simulation, it kind of does. So yeah, that's just one last interesting thing I had to input.